If we consider the reaction where water turns into, but it forms an equilibrium, hydrogen ions plus hydroxide ions. Water's a liquid. Got aqueous hydrogen ions, aqueous hydroxide ions. If we wanted to write an expression for Kc for this equilibrium, it would be, as always, Kc is the concentration of the products divided by the concentration of the reactants. Now, in this particular equilibrium, many millions of times more water exists than the hydrogen ions and the hydroxide ions. In fact, we can kind of see that the concentration of the water is like so massively big that we can actually exclude it altogether from the equation. So what we do is we put a line through it. And this means that we rewrite the equation and we call it Kw. And Kw is equal to the concentration of the hydrogen ions times the concentration of the hydroxide ions. And this is known as the ionic product of water. Now, as you're aware with equilibrium constants, they are constant so long as the temperature is constant. And it just so happens that the equilibrium constant that we're talking about here, the ionic product of water, has a value of 1 times 10 to the minus 14. And that would be moles squared decimeters to the minus 6, because we've got moles per decimeter cubed times moles per decimeter cubed, because it's got to be the two concentrations times each other. So it's 1 times 10 to the minus 14, and this would be at a temperature of, you've guessed it, 298. Standard conditions is 298 Kelvin, or roughly 25 degrees C. It's 1 times 10 to the minus 14. Now, you might be thinking, oh, how am I ever going to remember that? Well, the good news is you don't have to remember it. They give it to you in the exam. But also, if you remember, we're talking about pH at the moment, and pH, you all know from as far back as year 7, pH goes up to 14. So pHs vary between 0 and 14. So these numbers actually relate. So this is a number, this is the ionic product of water at 298 Kelvin. So it turns out we can use Kw to work out the pH of bases. So if we consider a strong base, for example, sodium hydroxide, when it's put into water, it fully dissociates, fully ionises, and turns completely into sodium ions and hydroxide ions. So we can see that for every 1 mole of sodium hydroxide solid that's put into water, we get 1 mole of sodium ions, and equally we get 1 mole of hydroxide ions. So if we know the concentration of the sodium hydroxide we put in, we'll know the concentration of the hydroxide ions, and if we know what Kw is, we can use this to work out the hydrogen ion concentration and then work out the pH. So, for example, if we had 0.025 mole per decimeter cubed sodium hydroxide solution, we could work out its pH, because we would know that this had, so we know it contains 0.025 moles per decimetre cubed hydroxide ions. And then we can use kW. So if we know that kW is 1 times 10 to the minus 14, and that's our hydrogen ions times the hydroxide ions, then if I want to work out the hydrogen ions, then I need to divide kW by the concentration of the hydroxide ions. So we know that's 0.025, and that's going to be equal to the concentration of the hydrogen ions. So if I plug those numbers into the calculator, I get an answer of 4 times 10 to the minus 13. Again, I remind you, I can't stress this enough, how important it is that you get to grips with your calculator over these. It is really, every calculator you use has a slightly different way of entering the numbers for dealing with things with powers and logs. So it is really worth making sure that you're used to using the same one at all times. So if our hydrogen ion concentration is 4 times 10 to the minus 13, if I want to work out the pH, I do exactly the same as I would do with an acid. So I know that pH is going to be equal to negative log to base 10 of the hydrogen ion concentration, which we've just worked out is 4 times 10 to the minus 13. So if I do negative log to base 10 of that, again, plug the numbers into my calculator, I get an answer of 12.397, so 12.40 if we're going to do it to 2 decimal places as the pH. So let's have another quick look at another example. So let's consider calcium hydroxide. Now, the reason I've chosen this as my example is that when it dissolves in water, we get 1 calcium ion. So, solid calcium hydroxide, 1 calcium ion, but we get 2 hydroxide ions. So, if I want to work out the pH of, let's say, for example, a 0.036, I'm making these numbers up, can you tell? Mole per decimetre cubed solution of calcium hydroxide, and I want to know what is the pH. So you might want to press pause and see if you can work it out before I go through the answer. Okay, so my hydroxide ion concentration is going to be equal to 2 lots of my calcium hydroxide concentration. So is going to be equal to 2 lots of 0.036. That's going to be 0.072 moles per decimetre cubed. And therefore my hydrogen ion concentration, which is the next step, so I need to do kW divided by the hydroxide ion concentration, is going to give me the hydrogen ions. So therefore I'm going to do 1 times 10 to the minus 14 divided by 0.072. And after plugging that into the calculator, I get an answer of 1.39 times 10 to the minus 13. And then if I know my hydrogen ion concentration, I can work out the pH. So pH is equal to negative log base 10 of 1.39 times 10 to the minus 13. which is equal to 12.6. Oh, no, sorry. Yeah, 12.857, so 12.6. Obviously, if these came out as acidic pHs, you know, less than 7, then you might ask questions because you were working them out from a base. So you've got, and you should know that it should come out somewhere between 7 and 14, otherwise you know you've done something wrong. So I'm just going to finish up with a final note about working out the pH of a neutral substance. So in the definition of water being neutral is that your hydrogen ions are equal to the hydroxide ions. So in neutral water, it ionises and you're going to get exactly the same number of hydrogen ions as you get hydroxide ions. And it's only when there's an imbalance between these two that something becomes acidic or something becomes basic if you've got more hydrogen ions or more hydroxide ions. So if you know that they're equal and you know that the value of Kw is 1 times 10 to the minus 14, so we know that Kw is equal to H plus times OH minus, then if you're given Kw and you know it's a neutral substance, then actually we can get rid of the OH minus and we can say that it's H plus squared. Kw is equal to H plus squared because H plus is equal to OH minus, we can say they're the same. So if I know what Kw is, I can work out the hydrogen ion concentration because it will be equal to the square root of Kw. Now, I've told you at 298 Kelvin, Kw is 1 times 10 to the minus 14. So if we work out the square root of that, we find it is 1 times 10 to the minus 7. And if I do negative log to base 10 of 1 times 10 to the minus 7, those of you that are good at maths won't even need to think about the calculator on this, you'll tell me that that will be 7. So that tells me that the pH at 298K is 7, but we've already discussed that Kw varies with temperature. So actually 7, which you all learnt long ago, was the pH of neutral water. Well, only at one temperature. The pH changes according to what the temperature is. Okay, I think that's enough for today. Probably time to start on the tasks.